Alright, hello. We are going to start chapter 16, which involves spontaneity, free energy, and entropy. So looking at if reactions will occur now. So we're going to look at just the entropy, enthalpy, and free energy component of this, or objective 1, and then we'll move on to how these things are used to calculate other variables. Okay, so the first section of this is the spontaneous process and entropy. Okay, so in order for something to be spontaneous, it needs to occur without outside intervention. It's got to just occur on its own. And these type of reactions or processes can be fast or slow. No information is really given about what the speed of the reaction is, just if it occurs without any outside assistance. Thermodynamics will predict whether a process will occur, but it doesn't really give any information on how long it will take or the speed of the reaction. That's all the kinetic stuff that we did in chapter 12. Spontaneity is controlled by entropy, and so that's what we're going to spend some time talking about today. So entropy, which we use a capital S to denote entropy, is the measure of molecular randomness or disorder. So how spread out, disordered, random are the particles. There is a natural progression in nature to go from order to disorders. For example, in general, is it easier to keep your room clean or dirty? Well, if you're like most people, it's easier to keep your room dirty, and so the natural progression is to go from an orderly system, a clean room, to disorder, and then you clean it again, and then it gets dirty, and it's this process. Entropy is associated very closely with probability, so if it's more likely to occur, it will. So if you think about gas particles spread out to take up the entire space in the container. That's more probable than them all staying together in one location. Okay, so let's look at an example. So we want to predict the sign of the entropy change for each of the following processes. So solid sugar is added to water to form a solution. Okay, well, if we have a solid, and it's being added to water to form a solution, what that means is that now the particles are going from being a sugar cube to being all spread out in a beaker of water. And so we would say that that's increasing the disorder, so I would say that S in this case is positive. Okay, our other example is that iodine vapor condenses on a cold surface to form crystals. So now we're going from all these gas particles being spread out all over the place to these crystals that are forming on a surface. And so now all of my particles are much more condensed. And so I would say that entropy has decreased. They're less random. And so now entropy is going to be negative, not positive. Okay, so section 2, we're going to look at entropy and how it relates to the second law of thermodynamics. So second law of thermodynamics says that in any spontaneous process, there's always an increase in the entropy of a universe. So if it's spontaneous, entropy increases. And this is of the universe. Now we usually break the universe into two parts, the surroundings and the system. And so we'll talk about entropy of the surroundings and the system, which is what we're interested in or what the reaction is. So the first law says that energy is conserved, but as you can see from the second law, entropy increases for spontaneous processes, and so this would mean that entropy is not conserved. So for our entropy of the universe, we have a total of, or sum of, the entropy of the system plus the entropy of the surroundings, just like we talked about with the two parts of the universe. So if the entropy of the universe is positive, this means that the process is spontaneous and entropy is increasing. Okay, so anytime you have entropy being positive of the universe, this means that the process will occur, or is spontaneous. If the entropy of the universe is negative, this means that the process is spontaneous, but only in the opposite direction. So in that particular direction, it wouldn't occur, but it would occur in the other direction. And if the entropy of the universe is 0, this means that the process has no tendency to occur or that the system is at equilibrium. Okay, well, temperature can also have an effect on spontaneity. So there are two characteristics of the entropy changes in the surroundings. So now we're just going to look at the surroundings, not the universe or the system. Okay, so the sign of the entropy of the surroundings depends on the direction of heat flow. Okay, so we talked about like exothermic and endothermic. So if a reaction is exothermic, then heat flows into the surroundings. So in terms of the entropy of the surroundings, this would be something that's positive. Heat's flowing into it. For an endothermic reaction, heat is flowing out of the surroundings, and so we would say that in terms of the surroundings, this is negative. Now, this may seem opposite of what we normally consider because usually we're thinking of entropy of the system. And so exothermic heat's flowing out of the system, which would be negative, but because it's flowing into the surroundings, it's positive in terms of the surroundings. Okay, the other characteristic of entropy for the surroundings is that the magnitude or the amount of the entropy for the surroundings depends on temperature. Low temperatures are much more greatly affected than things at high temperatures. So consider, like if you gave a millionaire $50, it wouldn't really make much of an effect. This is like a high temperature system. If you gave $50 to a poor college student, it would probably make a much bigger difference, and so this would be similar to a low temperature. Okay, so we can also talk about the relationship between entropy and enthalpy. Since we're talking about heat flow, let's talk about enthalpy. So for a process at a constant pressure, the entropy can be expressed in terms of enthalpy. Remember, enthalpy is the delta H. So change in entropy of the surroundings is equal to negative delta H, or enthalpy, divided by temperature. Here the delta H is negative because it's determined based on the system. Remember, we talked about for like an exothermic process, we would consider that to be a negative enthalpy because heat is leaving the system. But here we're referring to entropy of the surroundings, and so that's what we have to make delta H negative. So for example, if the reaction was exothermic, delta H would be negative, but since heat flows into the system, we want entropy of the surroundings to be positive. Oh, this should say surroundings, not system. Hold on, let's back up. This is surroundings. Okay, if the reaction is exothermic, delta H is negative. We know that because in terms of the system, it's leaving. But since heat flows into the surroundings, and we're talking about the surroundings, we need the entropy of the surroundings to be positive. So a negative from the enthalpy times the negative in the reaction gives us that positive, which is why the equation is negative delta H over T. Let's look at another example. So iron and carbon are used to reduce antimony in sulfide ores. And so we have these two equations, one with iron and one with carbon. And we have the enthalpy change for each one, or the heat of reaction. So we want to calculate the change in entropy of the surroundings for each of these at 25 Celsius and 1 atmosphere. Well, we know that delta S of the surroundings is equal to negative delta H over T. Well, we also know that 25 Celsius is equal to 298 K. And for our purposes, we are going to do temperatures in terms of Kelvin. So let's look at the first reaction involving the iron. We know that our enthalpy is negative 125 kilojoules. And we're going to divide that by our 25 Celsius, or our 298 Kelvin. And that's going to give us 0.419 kilojoules per Kelvin. And it's positive because we had a negative enthalpy. Okay, let's look at the change in entropy of the surroundings for the second equation. So here our delta H is 778 kilojoules over our 298 Kelvin, and that gives us negative 2.61 kilojoules per K. So larger value and negative. So in this second example, heat is flowing from the surroundings, because it's negative, to the system. And for our first example, because this entropy is positive, heat is flowing from the system to the surroundings, because our entropy of the surroundings is positive. Okay, so let's look at a summary of entropy. So here we've got the change in entropy of the system, which is what determines if something is, universe determines if something is spontaneous or not. And we determine that based on the entropy of the system and the entropy of the surroundings. When both are positive, this means that the universe entropy is positive and the reaction will occur, or is spontaneous. If both are negative, this means the universe entropy is negative and the reaction will only occur in the opposite direction. Now, the problem comes when we have one being positive and one being negative, because then it's more difficult to determine. And so we have to base it on the magnitude. If the delta S of the system, which is the one in this case that's positive, is larger in magnitude, then the process will occur. However, if the change in entropy of the surroundings is larger in magnitude, with it being negative, the process would only occur in the opposite direction. And then the opposite is true when the system is negative and the surroundings is positive. If the surrounding entropy is larger, then it will occur because it's the positive value. And we want entropy to be positive. Okay, the last part of this section is looking at free energy and how it relates to entropy. So we've looked at entropy itself, enthalpy and entropy, and now we're going to look at free energy and entropy. Symbol for free energy is a capital G, and this is named after the scientist who did some experiments involving this. And the relationship between these three variables is that free energy is equal to enthalpy minus the temperature times the entropy. So for a process at constant temperature, the change in G is equal to the change in H minus T, temperature, times the change in S, or entropy. We're going to drop all the system, universe, surroundings, because from this point on we're going to refer to all quantities in terms of the system, because that's the reaction that we're interested in. So if we do some rearrangement with this equation and our entropy of the universe equation, we get that the entropy of the universe is equal to negative delta G over T, and this occurs at constant temperature and pressure. So a process will only be spontaneous if the delta G is negative, because remember, entropy of the universe is what we're using to determine if something will occur. It needs to be positive, or delta G needs to be negative. So the free energy must decrease in order for a process to be spontaneous. So let's take a look at an example. Okay, at what temperatures is the following process spontaneous at 1 atmosphere? So we have bromine going from a liquid to bromine as a gas, and we know the delta H, and we know that the change in entropy as well. Okay, so we know, and we want to find the normal boiling point. Okay, remember, normal boiling point is the temperature at which the liquid and the gas states are at equilibrium, which means that delta G would be 0 if the system was at equilibrium. So if we take our equation, delta G is equal to delta H minus T delta S, this means that this value equals 0, and if we do a little bit of rearranging, that gives us that delta H is equal to T delta S, and then if I rearrange to solve for T, that gives me delta H divided by delta S, and then I can plug in my values. My delta H is 31 kilojoules per mole, and my entropy is 93 joules per Kelvin, capital K, mole. So I probably should change my kilojoules to joules. So instead of 31, let's times that by 1,000. So let's make that 3.1 times 10 to the 4th, and let's make that joules. Okay, so then when I divide them, I'm going to get 333 Kelvin. So that's my normal boiling point. That's the temperature at which liquid and solid are at equilibrium, and like we said, this is where delta G is 0. Well, let's look at if the temperature was greater than 333 Kelvin. In this case, delta S would be controlling the process, because this would be a liquid to a gas. Because if we raise the temperature, we're going to go from a liquid to a gas. This would involve more particles spreading out, which would increase entropy. If my temperature was less than 333 Kelvin, this is where delta H would be controlling the reaction, because it would become spontaneous in the exothermic direction, which would mean heat leaving the system. Okay, so delta H and delta S are dependent on temperature, and let's look at some situations. If change in entropy is positive and enthalpy is negative, then it's spontaneous at all temperatures. If they're both positive, then it's only spontaneous at high temperatures. If entropy and delta H are both negative, then it's only spontaneous at low temperatures. And if they're opposite, where entropy is negative, remember we want entropy to be positive, and the enthalpy is negative, then it's not spontaneous at any temperature, which means that the reverse process, which would make entropy positive and enthalpy negative, is spontaneous at all temperatures. So this would probably be something really good to put in your notes. Okay, we're going to practice these concepts and then go over these notes in class. Have a good day.